My mic was plugged into the wrong computer. Alrighty. Okay, so today we are going to it is a HyperX Quadcast. Like the only freaking mic that ever works for me, so it costs a bunch, so. But yes, it's cool, it's red. Okay. So I realize I actually skipped a section yesterday that I probably shouldn't have, but that's okay, we'll deal with it later on in this chapter. So I skipped the section on lattice energy, which is more thermochemistry calculations, so we'll skip that for now. I'll let you guys breathe for a minute without having to worry about thermochemistry right now. So let's go back to doing more Lewis structures. So let's take a look. Let's do carbon dioxide, and we're going to do it with the second method I taught you guys. So we're going to do it by looking at the electrons. So we have 4 plus 6 plus 6, which equals 16. We're going to assemble our skeleton with a single bond for each one. 16 minus 4, I can do it. 12. Yes. Here we go. There's 6 of them. There's another 6 of them. That is a really ugly subtraction. Alrighty. So we have now a Lewis structure, yes? If we look at it, we see, okay, our oxygen has 8 electrons. Other oxygen has 8 electrons. However, this poor carbon in the middle has only got 4. It's very sad. And so we're going to have to now look at one of the parts of what am I trying to say? Remember step 5 last time was adjust as necessary? That's what I'm trying to say. What we're going to want to do is we're going to shift a lone pair and turn it into a bonding pair instead. If we do that, I'm going to just redraw it because we're going to do this kind of step by step. So now if we look, oxygen has 8 electrons, however, carbon now has 6. So we have one more to do. And so we could plop that one in, or we could plop this one in. One of those two. The structures that you get would be this, or that. And so we are going to learn now how to pick between them. So we have now got our carbon that has 8 electrons. However, we have 2 potential options, and we're going to choose one. One of them is going to be better than the other. And so we're going to look at that. We're going to look at something called formal charge. And so you'll be able to calculate the formal charge for any atom within a Lewis structure. It's very exciting. And so it has got 3 parts. Let me just write that a little bit bigger. So I guess I should write this in black also. So it's your valence electrons, the number of valence electrons you have, minus the number of bonds you have, minus the number of lone pair electrons you have. So if we look at, let's look at this oxygen right here. The formal charge is going to be equal to 6, because it has 6 valence electrons. Oxygen has 6 valence electrons. It looks like we have 2 bonds on it, minus 4 lone pair electrons. So 6 minus 2 minus 4 equals 0. The oxygen on the right on that molecule is exactly the same, so I'm not going to worry about it. But let's look at the carbon now. I'm just going to label this as 1 so we all remember that. It's going to have 4 valence electrons, minus 4 bonds, minus 0 lone pair electrons, which also equals 0. We're going to do that now for the other side of stuff. I'm just labeling these so we can see the calculations for each of those atoms. So number 3 is an oxygen that has 1 bond and 6 lone pair electrons. So it had 1 bond, 6 lone pair electrons. Aha, we have something that's not 0. If we do the rest, and the last one, this tells us that in our structure here, we actually have a positive charge on this oxygen and a negative charge on that oxygen. So we did all those calculations. I'll scroll down in a sec so you can see them. And we see the one on the left, we saw that all of those had 0. And so Lewis structures that have no formal charges are going to be superior. So this one will be our kind of preferred form for carbon dioxide. I'm going to go ahead and redraw the molecule over here. We're going to see that this Lewis structure that we've drawn here actually has a positive and a negative charge on it. And while those charges do cancel out with each other, it's just more stable for a molecule to not have formal charges at all. We want the minimum amount of formal charges when we're doing our Lewis structures. So as a result, we're going to go with carbon dioxide that has 2 double bonds and not this 1 double and 1 single and 1 triple. Alrighty, let's go ahead and do some more. So we're going to look at some strategies now on how to work with these formal charges. Let's do this one. I guess I haven't talked about this particular structure yet. Notice we have a negative charge on it. For method 1 of our Lewis structures, the one where we just connect the valence electrons to try and satisfy our outer atoms, we always add electrons to outer atoms. For the other method, we would just add electrons to our total number of electrons. So in this case, we have a charge of -1, which means we're going to add 1 electron, right? Negative charge means extra electrons. It's a -1, so we only need 1 more electron. So I'm going to actually do method 2 first, and then I'm going to show you how to do this molecule or this ion with method 1. Okay? So we have the total electrons is 7 plus 4 oxygens plus 1 electron, because it's negatively charged, which equals, oh my goodness, 32? Let's see. 6 times 4 is 24, plus 8 is indeed 32. Skeleton time. We have used 8 electrons. We have 24 left. Six, 12, 18, 24. And so we have now used all of our electrons. We have none left. Looking at this, it looks like, okay, all of our atoms have octets. They have 8 electrons each. Everything looks happy. If we go ahead and do that, that would look like this. However, let's take a look at the formal charges of all these. If we do it for oxygen, that's 6 valence electrons minus 1 bond minus 6 lone pair electrons. Let me write bond, I'm sorry. 1 bond minus 6 lone pair electrons is -1. So in fact, all of these oxygens all have a -1 charge on them. They're all identical, right? They all have 1 bond and 6 valence electron or 6 lone pair electrons. If you look at the chlorine, it started with 7. It in fact has a charge of +3. So we can see here in this structure we have a ton of formal charges. Not ideal. And so we see that there is a way to mitigate these charges by forming multiple bonds. So what's going to actually happen is 3 of these are going to actually form double bonds with chlorine. It does not matter which 3, by the way. We'll talk about that in just a second. But if we do that, let's go ahead and look at what the structure would be after that. So if we take one of those lone pairs off some of those oxygens, we're going to see now, if you wanted to do the formal charges, we would see all of these would be neutral except this oxygen on the right. And in fact, because this is an ion that has a -1 charge, there's not going to be a Lewis structure that gets rid of that. So we're going to see that all those oxygens, I'm totally like out of space here, but we'll pretend, is now 6 minus 2 bonds minus 4 lone pair electrons equals 0. So the oxygens that have the double bonds are great. They're happy. No charge on those. And now our chlorine is going to have 7 minus 7 bonds equals 0. So that chlorine is also happy. And so it probably would be better to draw the Lewis structure on the right because of this. It has less formal charge than the others, than the previous one that we draw. That one had formal charges everywhere. The one on the right only has one charge on it, and that's necessary because it's an ion. Sometimes you won't be able to get rid of formal charges, by the way. You just want to have as few as possible, or like is the smallest possible formal charges. If we look at that structure, we could have done... Oh, go away. So this was the structure we got out, right? We could have instead done a double bond on the right instead of the top. Could have done that. We could have also, done it this way. I'm just kind of omitting the lone pairs for right now. I hope you forgive me. These are all equivalent structures. They are called resonance forms. So we could have made our double bonds on any of those 3 oxygens. Does not matter which ones. So as a result, all of these would be equivalent to each other. And so they're called resonance forms. And we often use this kind of double-headed arrow to illustrate that all of these are kind of interchangeable. So something I could ask you, not on exam 3, but on exam 4, would be how many resonance structures or resonance forms does the perchlorate ion have? And for that, you would be able to draw them and say, okay, well, I could have made I need 3 double bonds and 1 single bond from this. By the way, if you tried to make a triple bond on one of these, you'd end up with a positive oxygen, so that would not be good either. So typically making multiple double bonds is better than making a triple bond. But anyways, with this, you'd be able to come up with the resonance structures and understand that there are 4 of them for this particular ion. Exciting, I know. Let's take a look at method 2, by the way, or method 1 rather. Okay. So Shane, yeah. Did I not draw chlorine? Oh, how shame on me. Thank you for pointing that out. Yeah, those are definitely chlorines. I am sorry. Okay, with this, let's go ahead. Alrighty. So with the other method, we're going to get there in one step. So with method 1, when we have a negative charge, we are going to add electrons to outer atoms. it does not matter which outer atom because they're all the same. However, otherwise you would want to put it on the most electronegative one, but oxygen is, they're all oxygens, so it's okay. So, looking at this, let's give one of them an extra electron. All right, I'm going to put that right here. Okay, it does not matter which oxygen you give it to, I'm just putting it there. Okay, so that is our extra electron. So for method 1, again, we want to make bonds so that all of our outer atoms have paired electrons. So this oxygen now has everything paired. We're going to have to do the same thing for this oxygen. We want everything to pair off with stuff on the central atom. Lo and behold, I'm just going to do this so nice and neatly for you guys. Hey, look. What did we end up with? Right off the bat. Okay, it's chlorine. Thank you. I will remember that. Remember, we have our blue electron. That was the extra one that we got in there. And the others just kind of stay where they were. So this method always kind of already does the formal charge stuff for you, if that makes sense. Method 1, you do not have to necessarily look at formal charges. It's still always a good idea to, just in case. But most of the time, 98% of the time, you'll get the final structure on the first go. So usually works pretty nicely, in my opinion. Okay, so looking at this, again, we could have given that electron to any of the 4 oxygens, and whichever one we gave it to, that would be the single bonded one. And so that's how we would get our resonance forms from there as well. So we have 4 potential oxygens to give the electron to. And so we would have 4 potential resonance structures from that. Since this is an ion, we typically put it in brackets just to indicate that. And if we wanted to indicate the formal charge on it, we would see that this one is the negative. That's where the negative charge is on this particular ion. So again, you can use either method you want. I am partial to method 1 because it's faster, and you don't have to count. that's really what it comes down to for me. But again, a lot of you are probably familiar with method 2 a little bit more, and so you are totally welcome to do that. Okay, you'll notice this thing. Someone said yesterday, so we're going to say, yeah, all these oxygens have 8 electrons, but this poor chlorine now has 14 of them. Like, that's way more than what it would want. Too bad. Oxygen is more important because it's more electronegative. So it gets what oxygen gets what oxygen wants. So we have kind of there are 2 theories that kind of explain this. One is that chlorine has an empty chlorine has empty 3d orbitals, right? Chlorine is in period 3, so just quantum number wise, it should have an L of 2. And L of 2 means the d orbital, right? So it does have d orbitals, it just don't have anything in them. So technically, we could shove extra electrons into 3d orbitals. So it does have space for these electrons up there. Of course, it's not ideal, but oxygen gets what oxygen wants. There's a another kind of theory that's becoming more and more prevalent. It turns out this 3D orbital thing is kind of now becoming more and more passé as people do crazy calculations. We're going to see that chlorine is also just big enough to support all these electrons. So, but we're going to see as a result can be hypervalent. Hypervalent means it is above 8 electrons. And we're going to see that this can be, we're going to extend this idea to anything that's going to be in period 3 or more would be hypervalent. Could be hypervalent, not necessarily, but could be. So yesterday we had sulfur trioxide, which had 12 electrons. But if we look at this molecule, we have no formal charges on any of these atoms. So this is a good Lewis structure. And so we're going to see that this is pretty common to have hypervalent things. So phosphorus pentachloride here, the phosphorus will have 10 electrons. And so anything that's in period 3 or more can be hypervalent for these two reasons. Because anything in period 3 will have a empty 3d orbital. If it's period 4, it would have an empty 4d orbital. And then, as we know, as we go down the periodic table, things get bigger. We have more shells. We can basically hold more electrons as a result. Okay? Cool. So sometimes you will get hypervalent structures. They're not that uncommon. So a lot of the polyatomic ions will be hypervalent, and some are not. So, but most of them are, especially if they're in period 3+ thingies. Okay. Another example would be Shane's favorite molecule, xenon tetrafluoride. It has 2, 4, 6, 8, 10, 12 electrons on xenon. And so we're going to see that that's totally a thing. We could have... This is a fun one, by the way. Sulfur hexafluoride. If you ever get your hands on this, it's a pretty fun thing to do. So you know that if you breathe helium, it makes your voice all squeaky and high-pitched, right? If you try hydrogen, actually, it's even lighter, even higher pitch. But this gas here, sulfur hexafluoride, will actually make you very, very deep voiced. It's pretty cool. However, it's a bit more dangerous because it's a heavier gas. You have to make sure to really get it out of your lungs later, so that you can make more room for oxygen again. So it's pretty cool. Look it up on YouTube. Look up SF6 inhalation or something. It's pretty cool. So you can hear people talking with really, really low voices. So yeah, it's awesome. Okay, so we've gone through a bunch on Lewis structures. So you guys will have fun working on these. Hooray. Would you like to do a few more? I don't know how comfortable you guys are, if you've done these before or not, or what. If you want to do a few more examples, we can do that. Otherwise, we'll move on with our lives a little bit. Okay, so most fluid structures you're going to be able to do pretty easily with the rules, no problem. It's just that pesky adjust as necessary thing that is going to be annoying. We also have, sometimes we have what are called odd electron structures. These often are ones that contain nitrogen. For example, we have NO, nitrogen monoxide, or commonly known as nitric oxide, a hormone in our bodies that expands our blood vessels. We're going to see if we do this one, we're going to have some problems here. So let's go ahead and do it. We have 11 electrons. There is our skeleton. We have 9 electrons left. We're going to go ahead and give some electrons to oxygen. It's more electronegative. We always give to the most electronegative one. Those, again, are typically our outer atoms. So we have 3 electrons left. Yikes. So looking at this, our poor nitrogen has 5 electrons. Not quite enough. What's going to happen is we're going to end up pairing off another one of those. And making a structure like this. And we see we have an unpaired electron there that we're not going to be able to do anything with. If we look at the formal charges, though, it's got 2 bonds and technically 3 lone pair electrons. I know that that single one is not a lone pair, but it is a lone electron, I guess. So no formal charge. For oxygen, we have 2 bonds minus 4 electrons is 0. So this structure right here is the best we're going to be able to get out of it. This is known as a radical. Which is a unpaired electron. You'll see, lots of talk, of course, in media about free radicals and all that fun stuff. That's something like this. So nitrogen monoxide here, nitric oxide, is a free radical. It has an unpaired electron. These are usually pretty reactive. And something that is reactive is going to react with whatever is around it. So you're going to see, in biology class or whatever, that you're going to have antioxidants. Because these radicals will just kind of try and get an electron from anywhere. Often a target would be your DNA. That's not a good thing that you don't want to be ripping electrons off of, because that's going to completely mess up the structure of your DNA. And so you do have many molecules in your body that will be happy to kind of accommodate this. So they are okay to lose an electron. They often have a lot of resonance forms to help kind of make this radical feel safer, basically. Or they'll just, make double bonds or something and fix it that way. Or they'll just break apart themselves and it'll be okay. So radicals are not a good thing for us, but we have a lot of systems to deal with them. So all those antioxidants you get from your blueberries and your red wine and all that fun stuff. Oh, I just realized I left my coffee in the kitchen. I should get that. Antioxidants will help kind of mitigate this damage that you would get otherwise. So, alrighty. Not necessarily. Citric acid cycle doesn't have a lot of reductive compounds, unless you mean like NADH or FADH2, those would be able to quench the radicals. So it's not, I mean, it's kind of like the stuff that comes out of the citric acid cycle. Yeah. So yeah, you definitely, a citric acid cycle is a big old oxidation reduction thing. And electron transport deals with these radicals as well. And so you have oxygen there to kind of pick up the electrons at the end of the day. So that's why we need oxygen, right? So fun stuff. Alrighty. Does anybody have any questions on these? I don't want to kind of move on until we're feeling comfortable with them. So, and if you guys have a preference on the method that you like, I can just use that method in the future rather than just kind of switching between the two. So if most of you like the first method where we just connect the unpaired electrons, I'll just use that for all the examples. And if you like the second method with counting the electrons, I can do that too. So I'm going to get my coffee real quick. Y'all can write all your questions out. Yes, we can. Alrighty, let's do that same molecule then. So remember, method 1, we want to kind of make our outer atoms happy. And while this may not be obvious what the outer atom is, remember outer atoms are typically the most electronegative. With the exception of hydrogen. Hydrogen is always an outer atom, even though it is not electronegative. So if we look at these, oxygen is more electronegative than nitrogen, right? We've seen that before. So we want to make our outer atom happy by bonding things together. And so here we can see we're going to be left with that one electron unpaired on nitrogen. And that's just what it's going to be. So if we try to now bond that with oxygen, we would turn oxygen into a radical. And that would be not as ideal. So because oxygen is... Well, let's go ahead and look at it. So this is kind of what we end up with if we do it that way. If we tried to do it another way... Oops. If we tried to do it where we react, if we treat the nitrogen as our outer atom, we end up getting this nonsense. I guess it's not necessarily nonsense, but it's just because oxygen is more electronegative, it's going to be less stable. So nitrogen is going to be the better choice there. Just the way it is. So we want our less electronegative atom to accommodate the radical. So that's going to be nitrogen in this case. I do want to show you one more example that's kind of a unique case with the method 1. Yeah, I like method 1 as well. There is just one problem with it, and that deals with one particular compound, or one ion rather, nitrate. This one is I think in all the ones that I've done, this is the only one. This is the only problematic ion for method 1. So if we go ahead and look at it, oops, too many electrons. I'm actually gonna just redraw this for neatness. Okay. So if we, oops, not enough electrons there. There we go. Everyone's happy. Let's give one an extra electron. How about you? If we go ahead and do this, we'll get the following structure. However, we have done something naughty here. Anybody have any idea what we've done that's not allowed? What is not allowed with this Lewis structure? Where is nitrogen on the periodic table? Yeah, nitrogen cannot have more than 8. It is in period 2 only. It does not have a d orbital to throw things in. And it's also really small. So what we're going to have to do is break one of these double bonds. We're not going to be able to have that many double bonds. And so what we're going to actually have to see is that nitrate would look like this. We would basically, we're kind of doing the little like opposite there. And if we do our formal charges, we're going to see we have negative, positive, negative, which overall is -1, which is what nitrate is. No way to get around that. Nitrate is a special one. By the way, for all of these, if you want to, here, can I do this? Let's see. Why is, okay, let me get rid of it. Delete the, oops. Okay, will this work? Nope. Okay, let me just add one more window here so we can see what I want you to see. That's what I want us to see. Oh god, my mic is in the way. Okay. If we look at nitrate, we're gonna see I'm not BSing you about any of these structures. We see that we're going to have 3 resonance forms, right? We saw we had 1 double bond, 2 single bonds, and we had those formal charges there. All this stuff is, excuse me, it's all there. We see sulfur trioxide again. We see that it's hypervalent. We saw that nitrate is not hypervalent. What other fun ones have we done? Let's see. What was another hypervalent one we did? Or, I know. We can look at this guy. Oh, that's a bit strange. Usually it's typically drawn with the radical. This one they've kind of kept the radical partially between them. It's a bit strange. Oh, I know. We did perchlorate. We're going to see perchlorate is kind of the same way. Where are the Lewis structures? They're not here. When you see these kind of hashed bonds, that's just a way of combining all the resonance forms into one. So it's saying our double bonds could be on any of those. And so it doesn't really matter. But if you just Google it, you'll be able to see like the actual Lewis structures for most of these things. Usually Wikipedia is pretty good about it, but apparently not today. So there you go. So you can check your answers basically on Wikipedia or on Google, but always take everything with a grain of salt, right? Never just blindly trust the internet, unless it's me. I'm on the internet. Ouch. Okay. Alrighty. Any questions on these Lewis structures? All right. You asked for it. I have an example from the book that I want to do. Okay, so we'll come back to this stuff tomorrow, but I'm going to hop back in time now and pretend I did this yesterday. So this is not the stuff that would be on your exam. This is still stuff for like Lewis structures, the Lewis structures chapter. So we're going to learn about lattice energy. So you remember briefly yesterday we did the like, oh look, here we go. Oops. And we talked about the electron affinity and the ionization energy. Remember we had, was it solid? I don't remember. Actually, it's probably gaseous. Usually these have to be in the gas form, but whatever. This was the ionization energy. Actually, I don't, I'm just going to hide the states because I don't remember which one we did. And then we had half of chlorine plus an electron turning into chloride minus, right? And so we saw that this was ionization energy. And this was electron affinity. We saw that the ionization energy was, I have it here, 496. And the electron affinity for chlorine was, where are you? Negative 349. If we tried to put these together, if we were to try and put those together, we would say, okay, we're going to put delta H1 plus delta H2. You thought we were done with thermochemistry, didn't you? That's funny. Okay. We do that, we get, what is that? 147? However, we know that sodium plus chlorine react very readily together. It's actually quite exothermic. It's explosive. But our calculations here, whatever it happens to be, I probably got the number wrong, but it's endothermic. Exothermic. The reason for this is the ionization and electron affinity those are more theoretical things that, we're stripping our electron or throwing on our electron kind of in isolation. But it turns out we have a whole bunch of other processes that are happening together that actually make this quite exothermic as a result. And that is going to be what's called the lattice energy. So the energy of the negative and positive coming together is really what's going to drive this reaction to happen. And so lattice energy is going to be the energy to break a solid ionic compound into gas ions. So that would be, for example, this reaction. This would be how we would display the lattice energy. And so the lattice energy for this is the delta H reaction for this. That's what lattice energy is. So for that reaction that I've drawn there, we have solid sodium chloride turning into gaseous sodium ions and gaseous chloride ions. That delta H for that reaction would be equal to the lattice energy. And so we're going to want to see all the reactions that are happening here. So let's go ahead and have a look. It turns out that overall, this reaction has a delta H of negative 411 kilojoules, right? We would expect metal and non-metal coming together. That's going to be exothermic. Especially, we know sodium is very reactive, chlorine is very reactive. We would expect this to happen like immediately, right? And if we were to look this up on our, heat of formation table, we would see, yeah, it's negative, highly exothermic reaction. So let's see if we can't figure this out. So with this, oh my gosh, I'm going to have to use our book because this is a very long problem with lots of delta H's that I am not going to look up. So let's go ahead and look here. So if we're going to see that we're going to try and calculate the lattice energy for this particular compound, for this idea. Actually, I don't think we're going to have time to do this problem right now. It's okay. We can go 5 minutes over. Or should we just do it tomorrow? Actually, let's do it tomorrow. Because I would rather you let the Lewis structures kind of settle in your brain. So we'll just end a little bit early then, instead of going a little bit late. So we'll just continue this on Wednesday. Okay? If you want to try and give this a shot, this is the lattice energy reaction that we're going for. We're going to have to use a bunch of reactions and kind of our Hess's law idea for this process. So there's a whole bunch of reactions we're going to deal with, which is going to be, some of these are going to be, for example, and we're going to have a whole bunch of reactions like this that we're going to put together. So let's do this tomorrow and focus on your Lewis structures for now. So we'll stay on that end. Okay, I did post homework yesterday for your periodic trends. So that'll be due on Saturday. I will try and get the answer key for your last homework. I'll try and post that today if I have the time. So, and then maybe I'll start grading. Hooray. With that, we'll pick this up tomorrow. So I'm going to just use the same notes tomorrow. Or actually what I'll do is I'll just copy this section onto the... you know what, let me just do that now, actually. Can I do that? Oh, forget it. We have just too much. Okay. Any questions, by the way? Avoiding the lattice energy stuff for right now. We'll talk about that tomorrow. I realize I put something in our thingy. We're not going to need this till next chapter. So in this particular book, they teach this part after in a separate chapter. So I'm used to teaching it at the same time, but I guess we're doing this next week. So you can ignore this one for now. Alrighty. Well, in that case, I guess I'll see you all tomorrow. So have fun on your homework. Yeah, it's mostly conceptual stuff. Yeah, today is quiet. I think we're missing Tyler and Kevin, it looks like. Kevin might be here, but without a lot of calculations, he gets very sad. So, you know, I don't know, Tyler's probably snailing it up somewhere. So, but that's okay. Okay, well, yeah, go ahead and work on your homework. It's mostly conceptual stuff, so there's probably a good bit of writing you're going to have to do. So, that's okay. Shane, you can dominate the conversation. That's all right. But yeah, so I would definitely take a look. Don't leave that till Saturday because while the problems are not difficult, they do require a good bit of like explanation. So since it's all conceptual stuff. Okay. With that, I guess we're done for today. So I'll see you all tomorrow. Alrighty, take care.